Good afternoon, everyone. We will begin the webinar shortly. Thank you. Good afternoon. Welcome to the IPA Power Hour webinar on green hydrogen, exploring pathways to decarbonization. First, let me introduce myself. My name is Megha Hamal, and I'm the Communications Manager for the Illinois Power Agency, and I will be managing this webinar today. To get started, let's go over some housekeeping items. To reduce any background noise, all participants are muted upon entry. We have also recorded this webinar. A recorded version of this webinar will be found on the IPA website under About IPA and Events. We've also enabled live transcript for the meeting. If you wish to hide the live transcript button, you may click on the live transcript button at the bottom of the Zoom window and then hide subtitle. Also, please feel free to submit questions at any time during the webinar. We will be taking questions towards the end of the webinar, and you can use the chat function or chat window to submit your questions. A couple of points I want to emphasize. This webinar is for general education. Nothing that we are presenting is necessarily the position of the IPA or the entity that is presenting at the session today. Also, we will not be answering any questions related to the 2022 long-term plan, which is with the Illinois Commerce Commission for approval. Lastly, we will be sending a quick survey after the webinar is completed. We always welcome your feedback. Now, without further ado, let me introduce our speakers for this session. Our presenters for this session are Sarah Duffy, Associate Legal Counsel at the Illinois Power Agency, and Patrick Malloy, Manager with the Climate Aligned Industries Program at RMI. RMI is a nonprofit whose mission is to transform the global energy system to secure a clean, prosperous, zero-carbon future for all. At RMI, Patrick's work includes leading research into hydrogen adoption in the shipping and fertilizer sectors, as well as coordinating the Green Hydrogen Catapult's work on hydrogen hub development. Patrick has worked extensively across the energy sector. Previously, as part of RMI's mining team, he led work on mine site remediation of on-site renewable resource development. Thank you both for joining the session today and agreeing to participate. We really welcome that. Now, I would like to give you all a quick introduction and scope of the Power Hour webinar series. As you all know, Power Hour is a series of educational and informative presentation on a wide range of clean energy topics and emerging issues. Today's Power Hour is on green hydrogen, and we will provide an overview on what green hydrogen is all about, policy and industry developments across the globe, and opportunities for Illinois. As I mentioned, this webinar is only for education purposes, so we will not be answering any questions about the 2022 long-term plan or proposal made by the agency in the plan, which is currently with the ICC for approval. Here's a quick snapshot of Power Hour webinars that are taking place in June and July. If you have not registered for the Power Hour webinar, please do so. And the registration link is on the screen. A quick overview about the Illinois Power Agency. We are an independent state agency created under Illinois law in 2007. We are responsible for developing and implementing procurement plans for electricity supply for utility customers. These are your residential and small commercial customers of Illinois electric utilities that have not switched to an alternate electric supplier. And we're also responsible for developing and implementing renewable energy incentive programs. And we oversee the Renewable Portfolio Standard, which is a public policy designed to increase the development of renewables in Illinois. So this concludes my portion of the presentation. Now I would like to introduce Sarah Duffy, Associate Legal Counsel at the IPA, to provide a broad overview on green hydrogen, and she will be also talking about prospects and challenges of green hydrogen economy. Sarah.
Thanks, Megha. Welcome, everyone. This is a little bit of a novel Power Hour series webinar, since it's on a topic that is still developing not only in the US, but in Illinois. So since we don't have a lot of existing policy and law to talk about already, we wanted to give an update on, or an overview of, what green hydrogen is, what's coming down the pike on this, and what the opportunities in Illinois are as we look forward towards continuing the state's path towards a decarbonized economy. So I'm going to give an overview of green hydrogen generally. I'll toss it to Patrick to give some more detailed information on what the green hydrogen economy looks like today, and what some other regions are doing on policy and economic structures. And then he'll pass it back to me, and we'll take a deeper dive into why Illinois might be really well suited to becoming a leader in green hydrogen in the US. Next slide, Megha. So first of all, what is green hydrogen? So hydrogen obviously is a gas. Hydrogen gas can be used as a fuel source. It can be burned like natural gas can to provide a heat source. And generally it has very little environmental impact just from its end use. However, to produce hydrogen gas may cause some environmental impact. And so people in the climate space and generally in the industry have developed sort of a classification for kind of an informal rating for hydrogen gas, depending on the environmental impact of the way that it is produced. So when we say green hydrogen, we mean a hydrogen that is produced so that it has little to no greenhouse gas emissions or environmental impact. Next slide. So in terms of why this is important and why the Illinois Power Agency is even talking about green hydrogen, mitigating climate change for the most part is about energy sources. And in Illinois, we've done a lot on tackling the greenhouse gas emissions of our electricity sector, mainly through the programs administered by the Illinois Power Agency. But in order to really fulfill the decarbonization that we've set out as a policy of the state, we need to think about the energy that's used outside of our electricity system. And we also need to think about how to balance our electricity system when we're using more and more sources like wind and solar that are only online in kind of certain times of the year and certain times of the day. So to fill that gap that we right now use fossil fuels for, hydrogen could be a zero carbon solution. When it's burned, its only byproduct is water. And so if we use emissions-free methods of production. It's a completely zero carbon process. It's already being used in a lot of industrial processes as a feedstock. So it's already been proven as an industrial fuel source, and also in processes in chemicals and fertilizer production. Additionally, it could, as I said, complement the renewable energy sources we use on our electricity grid as a potential to balance out those intermittent sources. So it basically adds flexibility as a decarbonized fuel source, and a little bit more predictability to complement the current economically and commercially available renewable energy sources. Next slide. So as I mentioned, there are a number of ways we can produce hydrogen, and we have kind of, and by we, I mean the industry and climate advocates and researchers have informally dubbed these by color to kind of as a shorthand for the fuel source and the environmental impact. So currently, the most common way to produce hydrogen is using fossil fuels, mostly through natural gas in a process called steam methane reform, commonly referred to as gray methane. This is currently commercially viable. It's used in a lot of heavy industry, basically combining high temperature steam with natural gas to produce hydrogen, and also has some process and combustion emissions as well. So a couple of sources of greenhouse gas emissions from the gray hydrogen. One way to abate that would be to marry that with carbon capture and sequestration. This is referred to as blue hydrogen, essentially the same process, but with an added carbon capture system at the end, and depending on the extent of the capture of those emissions, that can reduce the emissions from production of hydrogen by 50 to 90%. In terms of zero emissions production methods, basically this would be through electrolysis, using electricity to split water molecules to produce pure hydrogen. And in that situation, you have to use zero carbon sources of electricity in order to have zero emissions. So this would either be through nuclear energy or renewable resources like wind, solar, hydroelectric, or other zero carbon electricity sources. So when using those, the entire production chain and its end use turn it into a zero carbon fuel source. Next slide. So this is a quick overview of kind of the main differences between these various production methods. So looking at the fuel type that they're using, the cost of these production methods per kilogram of hydrogen gas, and then the carbon emissions per kilogram of hydrogen. As you can see, there's a range for the cost per kilograms, and those ranges get bigger as we go to the right of the table. So the cost per kilogram of gray hydrogen is pretty well known because that's already in use widely in the industry. For blue and green hydrogen, the range gets larger because there aren't a lot of commercial applications of these methods. And so it really depends on the capital costs and the cost of electricity in the area and other variables. For nuclear, it's a bit harder. I wasn't able to find actually reliable estimates of the cost, but it would be essentially, I think, probably similar to green, maybe a little bit higher, because nuclear electricity is usually the most expensive type of electricity available to the grid. In terms of costs or CO2 emissions, you can see that blue hydrogen will reduce the per kilogram carbon emissions significantly, but it really depends on how much of those emissions get captured by the CCS system. Next slide. So, given all of that, I mentioned earlier that there are a lot of applications where electricity is not the best technical option for powering different activities in the economy. And right now we're using fossil fuels for those, but this is where hydrogen can really be a nice solution to those gaps in our decarbonization plan. So the three main applications, and this by no means captures every potential use for green hydrogen, but these are kind of the main buckets. Transportation is a really important one. I think everyone's heard of the potential for hydrogen fuel cell cars. That has not really been growing to scale in the way that electric vehicles have in passenger vehicles, so vehicles that people buy for just personal use. But for things like long haul trucking, rail transport, freight shipping, marine shipping, things where electric batteries and having to recharge actually make it a lot more technically difficult to use electricity as a fuel source. Hydrogen fuel could be a really good solution if the cost can come down and some other challenges get addressed. Additionally, hydrogen actually has more energy per unit mass. So a kilogram of hydrogen can actually fuel a vehicle further than a gallon of gasoline. So it does have a lot more potential as a solution for these kind of long distance transportation sectors. In heavy industry, there are a lot of processes that cannot be electrified because they require such extreme levels of high temperatures. And there are also just some chemical processes that need to happen that cannot be electrified. And so hydrogen could be a good solution for filling that gap as a decarbonized source of energy. And then finally, I mentioned earlier energy storage. So we're adding a lot of wind and solar to our electric grid across the United States. And so if you pay attention in this space, you'll probably be familiar with the issue of storage of that energy for off-peak use. So when we have times where we are producing a ton of electricity from solar and wind that is above the need for electricity, how do we capture that and save it for times when the production is lower but the demand is higher? Right now, a lot of people are investigating large-scale battery storage, but if we could offtake some of that electricity produced for free by solar and wind power and use it to produce green hydrogen that we can then physically store for later use when electricity demand is higher, that could be another solution if to complement batteries or in areas or in case batteries are too expensive or anything like that. Hydrogen can be used to generate electricity, much as natural gas is used in combustion turbines. So that's not the highest value use of hydrogen because solar and wind are so cheap when they are available. But it could be a good balancing method for those kind of off-peak hours. Next slide. So as I have laid out, there are a lot of benefits of hydrogen. So why aren't we already using it all over the place? Well, it is a lot, there are a lot of challenges in scaling it up. Unlike solar and wind as decarbonized energy sources, those get connected to the grid and the end user has no knowledge that they're using wind electricity versus electricity from coal or electricity from gas. The infrastructure is already there and it's completely complementary or easy to kind of integrate those. Not necessarily easy, but easier. From a hydrogen perspective, it's not quite as simple to just kind of switch out natural gas for hydrogen gas, and also the production is different. So three major challenges to large-scale use of hydrogen. I mentioned storage. Storage is a challenge because hydrogen is a very low density gas. And so in order to store enough of it to get the energy that we need out of it, you either need to have a huge amount of storage space or you need to condense it somehow, which requires high pressure or very low temperatures. And so there's a lot of work going on developing storage techniques that are efficient, that are safe, using, having such high pressure tanks and storage facilities could pose safety risks. And so developing those technologies is something that still needs to be sorted out. In terms of transportation, unlike electricity, again, not everyone is plugged into a pipeline that they can easily access. And the applications obviously are spread out. Even industrial hubs are not all next door to each other and need to have some sort of distribution system and on-site storage. There's potential for using existing natural gas pipelines for transportation, but it's unclear how those materials would respond to pure hydrogen gas as opposed to natural gas. There's also potential on railway and trucking, but again, safety hazards in terms of having highly pressurized storage and tanks traversing those routes. Then we come to cost. So all of those elements of the supply chain would add on to the cost, on top of the cost of production that we talked about earlier. And electricity prices will also factor into them, as will natural gas prices. So, and then on top of that, there's also some capital cost on the end use side. Obviously, the cost of designing a hydrogen fuel cell truck that can cross the country, or designing the technology to swap hydrogen for natural gas in an industrial process. You wouldn't be able to use the exact same equipment. So there are a lot of costs involved in the transition. Those all still need to be brought down. And that's, I'll talk about a little bit later about some of the initiatives that the Department of Energy is doing to try and stimulate some of that research and development to bring those costs down. Next slide, I think that might be it for me for now. Yep. So I'm going to pass it to Patrick and he can give even more detail now that you have the baseline, most basic elementary things from me. Patrick who is an actual expert in this, can discuss more about what's going on in research and policy.
Thanks, Sarah, and thanks, Megan, and thanks everybody. Glad to be with you today. Patrick Malloy, I'm manager of the Climate Aligned Industries program here at RMI, and maybe a quick little bit about RMI, if we can click to the next slide. So our kind of work is aligned towards scaling transformative change in our global energy system with an objective of cutting our greenhouse gas emissions by 2030 by directionally 50%, and obviously getting that 1.5 degree aligned scenario. So I suppose as a first question, if we can click to the next slide, one of the things to note about hydrogen, and we all hear an awful lot about it, is that no matter what global energy scenario we look at across a range of every kind of major producer of scenarios, we're looking at a many multiple scale increase in the volume of hydrogen consumed every year. So right now, globally, we're directionally probably 120 million metric tons, heavily consumed within the petrochemicals and the fertilizer sectors. But as you can see kind of on this list, the kind of use case profile is certainly diversifying, but also from 120 million metric tons, even, IRENA, the IEA's more conservative scenarios are at least doubling that market. And actually the more optimistic scenario is pushing that towards 6-7x of our existing market today. And that translates into, maybe directionally in the high teens percentage of the global final energy demand. And I think fundamentally the point in all of this is that hydrogen will play a key role in decarbonizing certainly a lot of the hard to abate sectors, but because of its flexibility, it has application in a lot of other areas where we have existing challenges within specific systems. So if we could click to the next slide. So one of the kind of foundational points that's worth bearing in mind here is, why do we need hydrogen? Kind of why now? Well, that 120 million metric tons that I mentioned is about 2% of global emissions today. That gray hydrogen that Sarah mentioned earlier, it's about 12 kilograms of CO2 approximately. It goes up and down a little bit depending on how well the system's designed and run. But it's about 12 kilograms of CO2 per kilogram of hydrogen produced through that SMR process. And as mentioned above, all the major studies that you see, kind of promote hydrogen as a molecular pathway for certainly industrial decarbonization, as well as a lot of other use cases. We've talked about shipping and trucking there as well. Obviously, conversations around long duration storage as well. So the flexibility starts to be valuable in this decarbonized pathway. But where this is truly interesting is when we start to look at the actual downstream use cases and what role it can play in decarbonization. So steel emissions, approximately 8.5% of global CO2 footprint. We can move to a scenario where that is essentially removed. And that's by changing our process from blast furnace, basic oxygen furnace style systems to direct reduction of iron using hydrogen as the feedstock there. Ammonia, basically swapping out those SMR units and producing hydrogen through electrolysis with renewable energy and water. And then, as I mentioned, global maritime shipping, and these are the areas that we concentrate on, is a substantial body of emissions as well, but also one that uses heavy fuel oils now. And ammonia as a potential alternative fuel holds great promise. So if we can click to the next slide a little bit, more on the details and kind of why we're talking about these pathways now, maybe a little bit more than we have in the past, and that's linked to the potential for cost declines to be actually realized. And this is a little breakout. It's based off I think it was the IEA's initial capital stack for a PEM electrolyzer system. As you can see, the stack itself there, quite small, but then the balance of plant systems on the right, the power systems, the processing, the cooling, there's specific kind of areas where you can concentrate a transition and switch the kind of the profile in terms of cost of the deployed electrolyzer system. So Kevin, your question, PEM is a proton exchange membrane, or it's interchangeable with polymer electrolyte membrane kind of systems. So PEM is a smaller modular system, typically in 1 to probably 4 megawatt stacks. The other dominant technology you'll hear about is an alkaline electrolyzer system, and they tend to be much larger in physical size, and they're also a lot older technology as well. All of this is to say that as we stand here today, directionally maybe about $700 a kilowatt for a PEM electrolyzer kilowatt deployed. A couple of years ago, that's probably pushing towards $2,000, maybe $1,500, $2,000 a kilowatt. And there is very clear pathways and mechanisms and levers to push us quite rapidly towards a $200 kilowatt system. And that is, and there's an awful lot of debate about this, and I'm certain that folks on the call here have heard quite a bit about, are these realizable? Some of this is around manufacturing. It's a maturity of the production of components that go into these things. Some of it is about system design and improving it, and some of it's just down to deployment and building facilities that can produce these things with low error rates at large volumes, and things that aren't strange relative to every other sector. And if we can click onto just the next slide. This is something, and I'm going to speak to the right-hand graphic first. This is something that we've just seen in solar and wind, and you see a cost decline potential that's very, very similar. So we're following a very, very similar curve to these technologies that we've seen on the renewables deployment side, whether it be batteries or solar or wind, as I mentioned. But we're not necessarily doing anything radically different to the technology. There's certainly some changes to how they may be designed, or the materials might shift a little bit, but fundamentally this is about maturing and scaling the production pathways. And as Sarah mentioned earlier, our production price today, speaking to the left-hand graphic, maybe around $4 a kilogram. It's very much dependent on the capacity factors of the renewable energy that you have, and also, the actual cost of that electricity. Very reasonably, pathway to, $2 a kilogram in the next 5 years is certainly achievable. And in some places, that's achievable today, and we'll see that in a little bit. But the DOE also has its Earthshot's target of $1 a kilogram by 2030, and there's a reasonable reason for optimism around that potential, and we'll speak to that a little bit more in a second. So maybe the next slide, please. So I'm going to use a non-Illinois example, but one that should be indicative of kind of what the opportunities and the kind of potential here is. So looking at a Texas example here, and we have developed an optimization model that kind of looks at how we would design green hydrogen systems in various locations, given various kind of cost expectations, both in terms of the energy, but also in terms of the capital stack. So on the left-hand side, just an indicative price today, gray hydrogen coming in at $1.80 a kilogram. Depending, there's a bit of range in that, obviously, depending on your natural gas price and, the facility scale and whatnot. But as something just to hold in your mind as an indicative price. Depending on what your kind of natural gas price here is, and the cost and efficiency of the CCS that you have, that blue range that you see there is that blue line kind of running all the way across. And I think our range, it's $2 to $7 an MMBTU estimated. And it's just to give you a sense of approximately where these things kind of overlap and where they can be. But when we compare it today in this is 2021, so last year, and look at Western Texas, you can see that it's a $225 a kilogram for a green hydrogen production resource. And that's with a full storage stock and flow system. It's meant to be a scaled project. So this is a fully loaded price. And therefore, it's not quite there, but it's pretty close in Western Texas, where you have extremely strong wind resources and very, very good potential, right? Compare that to Houston, which is slightly different geography, obviously the same market. That's not quite in the money today, and that's down to a few factors. And I think primarily the point here is that when you start and you look at that $700 kilowatt equivalent system that I mentioned above, you are really looking to utilize your electrolyzer as much as possible to make the pricing work. What happens when we get to that $200 kilowatt and below, but around that mark, is the two columns here on the right. because what you start to optimize for is the electron, and you're looking for the lowest cost electrons you can get your hands on. I should also just flag that all of these systems and all these scenarios were entirely non-grid tied. So these are all kind of unconnected to any offtake from the grid, and are running on purely the capacity factors of the systems that you deploy, combination typically of solar and wind. But we also optimize for those in these two scenarios on the right. And what that leads to, very simply, is far more competitive green hydrogen potential going forward into the future. And you can see, that West Texas opportunity is still stronger, and its storage potential is still listed there, but it's suddenly very competitive, and certainly competitive with the lower end of that natural gas range as well. So we're not quite there yet, but the pathway there is not necessarily terribly far away. The other thing just to flag here in terms of information about this scenario, Texas is home to a substantial body of the hydrogen economy today in the United States. And it's about, I have it there on the right, it's about 3.3 million metric tons per annum. That kind of equates, depending on those capacity factors, to about 35 gigawatts of deployed electrolyzers. It's just dependent on how much you deploy and what performance you have in terms of the energy resources. Obviously, then also in Texas, you can get some pretty cheap wind. So that's that $20 megawatt hour scenario. And also there are existing pipelines, infrastructure, and storage that you can leverage there as well. All of these factors you have to take account of, all of these things you have to be aware of when thinking about these systems and deploying these systems. And that's where the use case aspect comes in quite critically, because if you're trying to convert a steel facility or a fertilizer facility, that availability of supply is critical. When we talk about fueling stations for vehicles, it's a more intermittent, so you can have a more stock and flow style scenario. But you are really designing kind of to what your use cases are today, because we do not have that fully scaled market where there is abundant supply and multiple offtakes. So that system design dynamic is certainly important. It is as important certainly for the power sector if there's a long duration storage aspect to be considered as well. So maybe into the next slide. So this just to take a turn and kind of speaks to a slightly different angle. A couple of years ago, we would probably not be having the same conversation about hydrogen in the United States as we are today. And that's to say that there's been an awful lot of movement very quickly here. Whether, and what I've listed here certainly is linked to the federal actions being taken and efforts, but certainly state governments are being proactive now as well. So, and that's worth noting. So obviously the Earthshot, which I mentioned, which is that $1 a kilogram target by 2030. There's an awful lot of work around standards and harmonization around those. And then obviously the bipartisan infrastructure law, which allocated around $8 billion to hydrogen hub development. It's also worth noting that I think it's through Build Back Better, but there's still a conversation about if that passes a hydrogen production tax credit of up to around $3. Certainly, green hydrogen would likely be the eligible producer for that $3 PTC. I can't speak to the nuclear option, but I certainly know that the carbon footprint aspect would drop that PTC. So the blue hydrogen routes would certainly likely be impacted by that if it were to pass. But looking around the world a little bit, it's no surprise to anybody, European Union has been incredibly proactive, and even all of a week ago, the Power EU announcement committing even more transitional kind of aspirations on the demand side. The Certify standard that's already applied has been developed, and that qualifies that kind of hydrogen footprint as to being green or blue, but I think it's a little more rigorous on the kind of actual molecular kind of construction of standards. But also efforts like H2 Global, which are looking how to build these international supply chains around a hydrogen economy. And certainly, looking to that future action in Europe, consumer targets or consumption targets and partnerships are certainly critical. And similarly, when we look to South America, Chile has been very, very proactive in the hydrogen space for a very long time, certainly looking to build itself into a future export market or exporter of hydrogen to other markets. So therefore participating in kind of organized RFPs, developing standardization that's compatible with those kind of consumer markets. And again, looking for regional partnerships and collaboration. One last one, Australia has a national hydrogen strategy, has been developing a guarantee of origin scheme around Australian hydrogen footprints, and then is certainly looking at consumption targets and blending requirements in terms of the domestic use. But they're also, developing very, very large scale projects in Western Australia with a target to export ammonia to Korea and Japan. And to basically be an export hub for a whole heap of different use cases in that market, or those markets, I should say. So what it's worth noting here is that as any entity, government, otherwise, is starting to kind of engage in this pathway and understand the opportunities, there's an awful lot of work that has been going on around the world and examples of where this can play a role depending on the constraints that exist in a given space or a given market. So lots of opportunities to learn lessons that have been maybe hard learned or just trial and error, and also to see the applications where pilots have been successful and where markets start to emerge given kind of certain constraints and criteria. I believe that is the last slide from me, but I'd welcome questions or whatnot. Sarah, I think back over to you.
Thanks, Patrick. That was really interesting and definitely added some depth to some of the stats that I had laid out in the beginning. But what I got out of that, first and foremost, is that this is happening, and other countries are moving forward, other regions are moving forward, and so it's a little bit of a get on the train or watch it pass you by situation. And for Illinois, I think I'll go over some exciting opportunities in a minute, but we are well placed to play a role in the development of the hydrogen economy in the U.S. And the state is aware of that and excited to kind of see if we can be an early mover in this space so that we can stake a little bit of a claim and get the benefits of that reduced cost of electrolyzers that is coming and commercialization that will allow us to kind of build up a robust economy. You can move forward to the next slide. So Illinois has already taken at least a first step in this direction. This spring, the legislature passed SB 3613, which is a hydrogen economy task force bill. It was introduced by Senator Ellman and passed on April 6th. The governor is set to sign it. I don't believe that has actually happened yet. And once that happens, it will be in effect. And I believe then they will begin kind of naming members to the task force and setting up convening schedules. Essentially, the goals of the task force are to do the types of research that Patrick was talking about, look at examples from other jurisdictions and report to the governor's office recommendations for how to best position Illinois as a leader in the US. That report is due by December 1st, 2022. So they have a little less than, I guess, maybe half a year to get together and start working on what they believe is the best path forward. The task force is quite broad, so it definitely represents a wide swath of interested parties in Illinois. Not just government agencies, but labor organizations, research entities, justice organizations, and business and trade associations. So looking at how this might impact not only economic sectors of Illinois, but also communities and other stakeholders that are greatly impacted by the energy sector, and also want to access the job opportunities that it might present. So one of the other goals, and if you can go to the next slide, we'll see there's an opportunity federally, and the Hydrogen Economy Task Force is specifically tasked with thinking about how Illinois might best access federal funding that could help pave the way to establishing a hydrogen economy. The first opportunity comes out of legislation that Patrick mentioned in his policy slide, the bipartisan infrastructure legislation that was passed last fall. Does include several funding opportunities to accelerate and scale up research on hydrogen production and use of hydrogen in end applications. So Illinois has already been the recipient of at least one. There was a award of a grant to Gas Technology Institute based in Des Plaines, looking at the use of a mix of ammonia and hydrogen in gas turbines in order to look at that as an advanced clean fuel. We're also looking at the upcoming Clean Hydrogen Hub funding opportunity. This is meant to support the creation of regional hubs for both hydrogen production and use across the country. It has been allocated $8 billion, so there's a lot of excitement around this one. They have not opened up the actual application period yet. They have not posted the formal request for proposals. So we're still waiting and are excited to see what the parameters of that application will be. They're looking for diverse feedstocks, diverse geographies, diverse end uses. So we'll talk a little bit in a minute about what that might look like in terms of what Illinois' best or advantages might be. But across the country, there are a lot of states looking at this and just hydrogen in general. New York State has already developed some grants to support green hydrogen microgrids that focus on environmental justice. And other kind of research opportunities for demonstration projects. I know that some Western states have come together, such as New Mexico and Colorado and Utah, to create kind of multi-state consortiums. So there's a lot going on at the state level across the country on this right now. You can go to the next slide. So Illinois is poised really well to be an active participant in this. So first of all, we have a large kind of existing supply of zero emissions electricity. You know, as we mentioned, it's unclear what the cost for nuclear-based electrolysis would be, but we have an excess of nuclear. We actually export nuclear in addition to using it within the state. And so we have the potential to, you know, use that excess electricity to produce hydrogen that we can use in state in a variety of ways. It's also, you know, we're the largest producer of nuclear power in the US. So if we want to look at whether nuclear could be a good source or an economic source for producing hydrogen, we're really well placed to be the site of that innovation. Next slide. In addition to that, we already have a lot of potential for application. So creating a market and demand for the product. We have a high concentration of facilities that already use hydrogen, such as ammonia production and other industrial processes. We already have gray hydrogen production facilities, so hydrogen producing companies are already based in Illinois. So there's already a robust market for the product. We just need to find economic ways of switching that production from gray to green. Next slide. And then finally, as everyone knows, Illinois is a bit of a crossroads. We have major transportation hubs, a lot of existing railways. On the right, you'll see existing carbon pipelines and fuel pipelines. Carbon pipelines would be obviously useful if there was going to be development of blue hydrogen, which involves carbon capture. And so we already have a lot of the infrastructure that could form a good foundation for the eventual commercialization of green hydrogen. I think this is my last slide. If you go to the next one. Yes.
Yes.
So
yep.
I think we can open it up to questions. I don't see any in the chat right now, but
Yeah, we're not seeing any questions yet, but we do have about 10 minutes, so we can give our audience some time to think of a question.
So I actually have a question for Patrick, maybe to kick us off while people are thinking. If we can go back to his policy slide. So you have them categorized kind of on policies to produce for the supply and demand and infrastructure. I'm wondering if there's another way that you might categorize these, and if you can think about kind of the type of policy in terms of whether we're looking at financial incentives, standardization of you know, metrics and certifications versus product standards. So just kind of some of the different types of policy mechanisms and what might be seeming to be most popular right now.
I'm sure you can. On the kind of the top of mind, I think, you know, at the moment there's an awful lot of concentration about standardization and understanding that as a, you know, that's critical for that demand side market, right? So consumers can understand what they're purchasing and understand and recognize that value. That's certainly one that's common across a lot of different places. Other than that, I think common points would be certainly you know, capex supports on the supply side, right? So that bipartisan infrastructure law, $8 billion, that's been spoken about quite a bit, and then mechanisms for supporting pricing, right, for final consumers to incentivize transition. Other mechanisms, you know, thinking of some of the work being done in India on policy around blending mandates and targeted utilization for specific industries. That's certainly a mechanism and a policy approach that has come into being as well. I think it depends on the market that you're in. I think it depends on what is a kind of familiar or commonly used policy mechanism in different markets. But certainly there is an entire breadth of tools and mechanisms being used right now to work out what is the most appropriate or what is the clearest way. And you know, some of the questions I think possibly about Europe might be interesting. You know, there's recognition now, certainly I think prominently Germany around importation and wanting to minimize that CO2 footprint. So the carbon border adjustment mechanism tool is certainly going to be an external facing policy that will have a consequence there.
Great, thanks, Patrick. Actually, we're getting tons of questions now. The next question is from Michelle Kang. The question is, can hydrogen be cost effectively produced using grid electricity, and how does that fit into the development of green hydrogen economy?
I'm gonna
So
let you take it. I think I can guess the answer, but you would probably be able to say it eloquently.
yeah, well, you know, fundamentally, when the technology pathway is electrolysis, um, and this speaks to that technology cost decline that I mentioned in the presentation. It fundamentally comes then down to the price of your electricity. So hypothetically, you know, depending on how much your grid electricity costs, yes, it could be competitive. It just depends, and there's certainly grids where there's time sensitivities around that. You know, I spoke to a Texas example. We've all seen the kind of variability in the pricing in that market, for instance. It just can depend. Um, I think in respect to the green aspect of that question, you know, the carbon intensity of grids is certainly a big factor there. And, you know, commonly right now, that would be certainly a hurdle in an awful lot of grids to kind of qualify for those green standards. We're still waiting on that guidance from DOE. I'm sure that will be forthcoming soon enough. But yes, in a lot of places, that aspect would probably be more challenging today.
Sure. Thank you. Another question is from Benjamin Reshi. Is it possible to blend hydrogen with natural gas to use existing pipelines and distribution networks? And if so, what's the highest percentage of hydrogen that could be used in existing infrastructure and equipment without major modifications?
Yeah, so fundamentally, yes. I think the guidance from NREL generally right now is something around 7% by volume blending. What's worth noting here is it depends on the quality and type of pipeline. So a specific set of pipelines could have a higher blend. Some wouldn't do so well with possibly even that blend. So having actually an integrity study of that pipeline infrastructure to understand that would be critical. The key issue here is that hydrogen as a smaller molecule has an effect on the pipeline's interior. It can cause embrittlement. It just depends on the steel quality, and it depends on the pipeline type and integrity. So you have to do that due diligence work beforehand. But as an approximate guideline, 7% by volume, sometimes less, sometimes more. But certainly in principle, you can blend it in existing pipeline infrastructure and use it that way. Albeit, you know, then taking it back out is another challenge then that you add, unless you're hoping to blend it into, for instance, gas turbines, in which case you have to modify or adjust the pipe or the turbine depending on what the blend is. So there's a series of potential questions that emerge depending on what you're trying to do.
We have another question from our very own, actually our first IPA graduate fellow, Hannah McCory, and she's asking, I've seen natural gas producers in Oregon propose converting existing natural gas pipeline to hydrogen. Would pipelines have the right pressure and width to do this?
Hypothetically, they could, and it's I suppose pressure questions come in for sure, right? You know, if we want to talk about moving hydrogen at pressure, then again, to the point, you'd want to look at that pipeline integrity and do a proper system survey on it. I don't know specifically Oregon, and therefore I couldn't comment on those conversions. But for instance, to use an international example, in the UK. Northern Gas Networks made a choice in Leeds many years before hydrogen was on the radar to convert their distribution system into polyurethane piping. And as a consequence of that, they can pipe hydrogen through it at 100% without any pressure or well, there's some pressure management constraints for sure, but without any conversion issues, bar changing burners on the home heating stoves and boilers. So it really comes back down to the integrity of the system and the volume and kind of what you're trying to use it for. But it's certainly possible there.
Okay, so we'll take one more question from Benjamin again. How much does the availability of water become an issue if we want to use hydrogen produced by electrolysis more widely?
Certainly, water use is something to be cognizant of. I would say that for the scaled facilities that we've kind of worked with people on, for instance, looking at desalination has been common enough, because at the scale of facilities, it's really not that troublesome. The capital volumes being deployed on these multiple gigawatt scale or tens of gigawatt scale kind of projects is not that big a deal. So that is one route that solves it. You have to be cognizant of it. It is, approximately 10 kilograms of water, directionally 10 liters of water, approximately, depending on the efficiencies. It's probably slightly more than that with losses, but it's not insubstantial, and it has to be managed. But also, if you are thinking about hydrogen use, if you put it through a fuel cell, you get water vapor back out the other side. We're not necessarily talking about destruction or kind of combustion necessarily in many of these use cases. But yes, there is a water use here that you have to be cognizant of, certainly.
Great. Well, thank you. I think it's almost 1 o'clock, so I want to wrap up this webinar. So on behalf of the IPA, I want to thank all attendees for attending this webinar. But above all, I want to thank our wonderful speakers, Patrick and Sarah, for sharing such insightful content on green hydrogen, prospects and challenges of green hydrogen for clean energy economy, and also providing a snapshot on global policy responses on green hydrogen. So thank you both for providing such wonderful content. We appreciate it. Well, that wraps up our presentation for today. Our next webinar will be on June 24th. So do please go to the IPA website and register for the webinar on June 24th, and we will see you then. Thank you all.